Welcome to this video here, and in these videos that I'm going to start, I'm going to show you how to solve for antiderivatives, or in other words, how to solve integral problems. Now, you may remember that evaluating an integral or finding an antiderivative is actually the inverse of finding a derivative. So if you've mastered getting derivatives, now it's time to master going the other direction. So let's take a look at the definition of an antiderivative. So first of all, I want to show you here that the function capital F of x is an antiderivative of the function that's lowercase f of x if for every x in the domain of f it follows that the derivative of the capital F is f of x. Now I like to show my students, start them out with just showing them some examples of some antiderivatives. So let's suppose that we have a function little f of x is equal to 2x. Now let me show you this. You know that the function x squared has derivative 2x. So therefore x squared would be an antiderivative of 2x. But we also know that x squared plus 5 is its derivative would also be 2x, since the derivative 5 is 0. So we'd have to say x squared plus 5 is also an antiderivative of 2x, wouldn't we? But what about x squared minus a number? What about x squared minus 7? Well, x squared minus 7 would also be an antiderivative of 2x, because the derivative x squared minus 7 is simply 2x. So therefore we would actually say that the antiderivative of 2x would be x squared plus any constant. And so when we calculate antiderivatives or indefinite integrals, we actually have to add the constant to the answer. Okay, so let me just do one more here. So suppose I wanted to find an antiderivative of x cubed. Well, let me pose that x to the fourth over 4 would be an antiderivative. Now if you take the derivative of x to the fourth over 4, you'll see that you'll get x cubed. But also if you take the derivative x to the fourth over 4 plus 100, or x to the fourth over 4 minus pi, you'll also get x cubed if you take the derivative of those. So therefore the antiderivative of x cubed would be x to the fourth over 4 plus a constant. So right now, I'm going to give you some rules in a minute, but right now I just want you to think backwards. See if you can come up with a function whose derivative is equal to x squared. If you can come up with a function whose derivative is x squared, then that function must be an antiderivative of x squared. Well, I claim that x cubed over 3, I claim that the derivative of x cubed over 3 would be x squared. You can check it, because if you take the derivative of this, you just get 3x squared over 3, the 3's cancel, and you get x squared. So since x squared is the derivative of x cubed over 3, then the antiderivative that I would use for x squared would be x cubed over 3 plus any constant. What about the constant function 5? Well, we know that 5 is the derivative of 5x. So therefore, the antiderivative of 5 would be 5x plus any constant. What about trig functions? How about cosine x? Well, we know cosine x is actually the derivative of sine x. So therefore, the antiderivative of cosine x would be sine x plus any constant. And then another one, how about secant squared? Well, we know that secant squared x is the derivative of tangent x. So therefore, antiderivative of secant squared would be tangent x plus a constant. And then here's a couple more here. 4x is the derivative of 2x squared. So the antiderivative of 4x would be 2x squared plus a constant. And two more here. 1 over x is the derivative of natural log of x. So the natural log of x would be an antiderivative of 1 over x. So the natural log of x plus c would be the antiderivative. And the absolute value is just to avoid having a negative in the argument of the log. And then this one, e to the x, well, we know e to the x is its own derivative. So if e to the x is the derivative of e to the x, then we can say that the antiderivative of e to the x is just e to the x plus a constant. Now I'm going to show you some rules for integration, but the most powerful rule, no pun intended, is actually the power rule for integration. So the power rule for integration is basically if you want to integrate the power of a function, then, like for instance, if you want to integrate x to the n dx, then you would you're basically reversing the power rule for derivatives. So what you would do is you would add 1 to the exponent and then divide by the resulting new exponent. So this rule works as long as n does not equal 1. As long as n does not equal -1, this rule works. Actually, if n was -1, the integral would actually be the natural log would be the result. Okay, but it works on any other value for n. So here I want to, and by the way, if you're not familiar with this, this is the definite integral symbol, and this symbol is actually what we use to get antiderivatives. Is we just simply use this integral symbol to get antiderivatives. So this symbol tells me I want to get the antiderivative for x to the 5th. Okay, so what's the antiderivative x to the 5th? Well, using this rule, the antiderivative, I would add 1 to the exponent, so I would get x to the 6th, and then I would divide by that same result, which is 6. And then, of course, you also add a constant. So the antiderivative of x to the 5th would be x to the 6th over 6 plus a constant. Okay, now here's another one, and on this one I'm integrating with respect to t, and since my function is a function of t, then we're okay. So let's integrate this with respect to t. So we'll add 1 to the exponent, and then we'll divide by the result. So that would give me 1/2 plus 1 is 3/2, so that would give me t to the 3/2, and then I divide by 3/2. But dividing by 3/2 is the same as multiplying by 2/3. So I'd have 2/3 times t to the 3/2, and then don't forget, you always add a constant when you find antiderivatives. And when I say find antiderivatives, that's the same thing as evaluating these indefinite integrals. These are indefinite integrals, and we'll talk about definite integrals later, but right now indefinite integrals, they're the ones that don't have the little numbers at the bottom and the top of the integral. So these are indefinite integrals. Okay, so this is the square root of x cubed. Well, let's rewrite this integral as the integral of x to the 3/2, because the square root of x cubed is the same as x to the 3/2. Then we'll apply the power rule. So add 1 to 3/2 and then divide by the result, 3/2 plus 1. And so that would give me x to the 5/2 divided by 5/2. And then, of course, you invert and multiply, and you get 2/5 times x to the 5/2. And then don't forget to add your constant. Notice I always add my constant when I evaluate one of these indefinite integrals. Okay, so here's another one. We have 1 over x to the 3/5, and that we rewrite that as x to the -3/5. And then we apply the power rule, so we get x to the -3/5 plus 1 over -3/5 plus 1, and then of course plus the constant. And then we say, okay, well, -3/5 plus 1 is 2/5, so we get x to the 2/5 divided by 2/5 plus a constant, and then dividing by 2/5 is the same as multiplying by 5/2. So we get 5/2 x to the 2/5 plus a constant. So this power rule is actually pretty simple power rule. Now remember, this rule only works when the individual variable is raised to a power. A little bit later, we'll talk about a general power rule that works when you have a function raised to a power. Okay, so here are some rules for integrals that you can use. If you integrate 0, you'll always just get a constant. So the integral of 0 is nothing but the constant. If you integrate a constant dx, and by the way, all integrals have to have this operator dx in it, or it depends on the variable. The variable might be t. If the variable's t, then it would have dt. But this is the differential that has to be in the integrals. But anyway, if you integrate a constant, you get a constant times the variable plus another constant. So if I integrate the constant 5, then that result would simply be 5 times the variable x plus another constant. Now, the constant multiple rule basically says if you integrate a constant times a function, that's the same as the constant times the integral of the function. So if I wanted to integrate 5x squared, that would be the same as integrating 5 times the integral x squared. And since the integral of x squared integrates to x cubed over 3, and you multiply that by 5, you just get 5x cubed over 3 plus a constant. And there's no reason to worry about multiplying the constant by 5, because even if you did, 5 times a constant would still be a constant. Okay, now we also have a sum rule that says if you integrate the sum of two functions, that's going to be the sum of the two integrals. So if I wanted to integrate x squared plus x here, then that would be the same as integrating x squared and then integrating x. So if you integrate x squared, you get x cubed over 3 plus a constant. And if you integrate x, you get x squared over 2 plus a constant. That's using the power rule on both of those. And we don't actually have to put two constants here, because we know the sum of the two constants is just going to equal a constant. So we just can do one constant here. All right, and then the same thing for a difference. Same thing. The integral of a difference is the difference of the integrals. So if I had x squared minus x and I had to integrate that, then that'd be the same as integrating x squared dx, and then subtracting from that the integral of x dx, and that would give me x cubed over 3 minus x squared over 2 plus a constant. Again, applying the power rule to both of these. And of course, I've already shown you the simple power rule here. So, you know, there's an example. X to the 5th dx is just x to the 5 plus 1 over 5 plus 1 plus a constant, which is x to the 6 over 6. Okay, so that's your basic power rules. Okay, now in the next video, I'm going to show you the basic integral rules for the trig functions, like the trig functions like sine of x and cosine of x and so forth.